Welcome to this tutorial on torch.compile, PyTorch 2's powerful JIT compilation feature that can significantly speed up your models. This notebook is based on the official PyTorch tutorial by William Wen, with additional plots, detailed explanations, and my own insights. And I'll guide you through how to use this feature effectively. We'll cover basic usage and best practices, see performance comparisons with visualizations, understand the advantages over TorchScript and FX Tracing, and dive into Torch Dynamo and graph breaks. Before we begin, make sure you have PyTorch version 2 or higher installed, and ideally an NVIDIA GPU like V100, A100, or H100 for the best speedups. You'll also need TorchVision, NumPy, SciPy, and Matplotlib packages. Let's start by setting up our environment and checking what GPU we have available. This code will detect your GPU and let you know if it's optimal for torch.compile speedups. We're also configuring Matplotlib for nice visualizations later. We can see that a GPU was detected with CUDA capability 8.6. This is not one of the optimal GPUs like V100, A100, or H100, so we're getting a warning that speedup numbers may be lower than expected. That's okay though, we'll still see improvements with torch.compile. Now let's explore the three main ways to use torch.compile. This is really the heart of what makes this feature so easy to adopt. The first method is direct function compilation. Here we define a simple function that computes sine of x plus cosine of y. We then compile it using torch.compile and call the optimized version. This is the most straightforward approach. Great, we can see the compiled function works perfectly. It returns a tensor with shape 10 by 10 and a mean value of about 0.55. Notice how there's also a message about no CUDA runtime being found, which is expected when running on CPU or certain GPU configurations. The second method uses decorator syntax. This is my personal favorite because it's so clean. We just add the torch.compile decorator above our function definition, and it automatically gets compiled when called. Perfect, the decorator syntax works just as well, giving us a result with the same shape. The third method is for neural network modules. We create a standard PyTorch module with a linear layer and RayLU activation, then call the compile method on the module instance. This compiles the entire module in place. Excellent, our compiled module produces output with shape 10 by 10 as expected. This shows that torch.compile works seamlessly with nn.module classes. Here's something really cool about torch.compile. It automatically compiles nested functions and modules. Let me show you what I mean. When we compile an outer function, any nested functions it calls also get compiled automatically. Here, even though we only explicitly compiled the outer function, the nested function gets optimized too. This is a huge advantage for complex codebases. We get a mean value of about 0.68, and the nested function was compiled along with the outer one. The same automatic compilation happens with nested modules. When we have an outer module containing an inner module, compiling the outer one automatically optimizes everything inside. Perfect, our nested module structure works flawlessly with shape 10 by 2 output. Sometimes you might want to exclude certain functions from compilation. PyTorch provides torch.compiler.disable for this purpose. Let's see how it works. Here we're using torch.compiler.disable to prevent the complex function from being compiled, while still allowing functions it calls to be compiled. This is useful when you have functions that don't compile well but call other functions that do. Great, we successfully computed the complex number operations with selective compilation, getting a result of approximately 4.47 and 5.83. Now let's get to the exciting part, performance benchmarking. We'll compare the actual speedups you get with torch.compile. I'm setting up utility functions for accurate benchmarking. We'll use CUDA events for timing when available, generate random input data, and use DenseNet 121 as our test model. This is a realistic model that's complex enough to show meaningful speedups. We're ready for benchmarking on CPU, since no GPU is available in this environment. Let's start with inference performance comparison. First, let's see how the initial run compares between eager mode and compiled mode. We're using reduce overhead mode for maximum speedup. Notice that the first compiled run will be slower due to compilation overhead. As expected, the first eager run took about 0.17 seconds, while the first compile run took 9.6 seconds. This includes the compilation overhead. Don't worry, this is a one-time cost, and subsequent runs will be much faster. Now let's run multiple iterations to get accurate performance measurements. We'll run 10 iterations and calculate the median times to get reliable statistics. Excellent results. After the initial compilation, we're seeing consistent speedups. The eager mode has a median time of about 0.122 seconds, while the compiled mode runs in 0.084 seconds. That's a 1.46x speedup for inference. This is quite good, especially considering we're not on an optimal GPU. Let me visualize these inference performance results to make them clearer. We'll create two plots, one showing performance over iterations and another showing the median comparison. Looking at the visualization, you can clearly see how the compiled mode consistently outperforms eager mode across all iterations. The time series plot shows the compiled mode running faster with less variation, and the bar chart highlights our 1.46x speedup. This is a significant improvement that you get essentially for free just by adding torch.compile. Now let's look at training performance comparison. We'll set up a training function that does a forward pass, computes cross-entropy loss, backpropagation, and optimizer step. Then we'll compare eager mode training versus compiled training. Interesting results here. For training, we're seeing a median time of 0.316 seconds for eager mode and 0.249 seconds for compiled mode, giving us a 1.27x speedup. Notice the warnings about graph breaks from the loss.item call. This is Torch Dynamo telling us it had to break the computation graph at that point. We could potentially get even better speedups by capturing scalar outputs, but the current speedup is already quite good. Let's visualize the training performance and create a summary of both inference and training speedups. The visualizations clearly show that torch.compile provides consistent speedups for both inference and training. We're getting 1.46x speedup for inference and 1.27x for training. These are significant improvements that can really add up over long training runs or when serving models in production. Now let's compare torch.compile with other PyTorch compilation methods like TorchScript and FX Tracing. This will help you understand why torch.compile is often the better choice. First, let's look at how different compilation methods handle data-dependent control flow. We'll create a function with control flow that depends on the actual tensor values, then test it with different compilation methods. We're ready to test different compilation methods. The key here is that our function behaves differently depending on whether x.sum is less than 0. Let's start with TorchScript tracing. This is one of the older compilation methods in PyTorch. TorchScript tracing works for the same input path, but fails when we take a different control flow path. It gives us a warning about converting a tensor to a Python Boolean, and the trace doesn't generalize to other inputs. This is a major limitation. Now let's try FX symbolic tracing. FX symbolic tracing completely fails with an error. It simply cannot handle data-dependent control flow at all. Even when we try to help FX by providing concrete arguments, it still has problems. FX with concrete args appears to work, but still fails when the control flow path changes. We get a warning that it couldn't add assertions to guarantee correct inputs. Now let's see how torch.compile handles this same function. Perfect. Torch.compile handles both control flow paths correctly. This is a huge advantage over TorchScript and FX. It can handle arbitrary Python control flow. Let's also look at how these methods handle mixed types and non-PyTorch functions. Here's a function that can take either a tensor or scalar as the second argument. Let's see how different methods handle this. TorchScript fails with a type error, expecting a tensor but getting a scalar. However, torch.compile handles it perfectly, returning the correct result shape. Now let's look at functions that use external libraries like SciPy. We're setting up a test with non-PyTorch operations. Here's a simplified example that shows how torch.compile handles external operations like NumPy interop. We're ready to test non-PyTorch function handling. Let's see how TorchScript trace handles NumPy operations. TorchScript trace fails to handle NumPy operations correctly. We get warnings about converting tensors to NumPy arrays and the results being registered as constants. Now let's try TorchScript and FX. Both TorchScript and FX symbolic trace have limitations with external calls and NumPy operations. This should be torch.compile handling the NumPy interop. Let me demonstrate how we can use a custom backend to inspect what torch.compile is doing under the hood. We'll create a custom backend that prints out the FX graphs that torch.compile generates. This gives us insight into how the compilation works. We've reset Torch Dynamo and prepared our custom backend for inspection. Let's compile a function with data-dependent control flow and see how torch.compile handles it by generating multiple graphs. Fascinating, we can see that torch.compile generated multiple FX graphs. The first graph handles the computation up to the conditional check, then separate graphs handle each branch of the if statement. This is how torch.compile handles dynamic control flow by breaking the computation into multiple static graphs. Let's analyze the graph breaks more formally using torch.dynamo.explain. We have two graphs with one graph break. The break happens at the conditional jump in line 4 of our function. This is exactly where we have our if statement. If we try to force full graph compilation without allowing breaks, let's see what happens. As expected, forcing full graph compilation fails because our function has dynamic control flow that requires graph breaks. This is an important concept to understand when optimizing your models. Let's check if a standard model like DenseNet can compile without graph breaks. Great news! DenseNet compiles successfully with full graph equals true, meaning it doesn't have any dynamic control flow that would cause graph breaks. This is ideal for maximum performance. Let me wrap up with a summary of key takeaways and best practices. Torch.compile is incredibly easy to use. Just wrap your function or module. You often get 2x or more speedup for both training and inference. Unlike TorchScript and FX, it handles arbitrary Python including control flow and external libraries. It automatically handles unsupported features by breaking graphs. For best practices, start with reduce overhead mode for maximum speedup, use full graph equals true to detect breaks early, compile at the highest level possible, and always profile to measure your actual speedups. Torch.compile is great for standard neural networks, models with dynamic control flow, and code using NumPy or SciPy interop. Consider alternatives for mobile deployment where you'd use TorchScript or extremely dynamic models with many graph breaks. Happy compiling. And that concludes our tutorial on torch.compile. Thanks for following along.